Hello, Chemistry 30. Welcome to week 3 of our distance learning. And we are continuing on in our redox chemistry unit, but we're getting into some of the application side of these redox reactions, which I always think when you start to see how things are actually used for, it ups the interest ante. So as per usual, if you've got questions, let me know, guys. I can arrange that we can chat back and forth on Google Classroom. We can do a video conference if you want. I can call you. We can talk on the phone. Whatever is going to help you to achieve success. Now, just a little bit of a disclaimer about this week. We've got 4 main concepts that we're going to be focused on, but in many ways, the assignment is one of those where you really want to go through, honestly, in many ways, the entire notes, the entire set of podcasts before you try to attempt the assignment. I tried to split it up in terms of a way that you could go step by step through the questions, but be aware that it's kind of a broad picture of look at the whole thing and now see if you can apply it. Anyway, I will still do 4 separate podcasts, otherwise they'll end up way too long. And our focus today is going to be on the voltaic cell. So voltaic cell, if you think about the beginning of the word volt, is essentially a way from chemicals that we can turn the potential energy in a chemical and in a chemical reaction and convert it into electrical energy, usable energy, which is pretty cool. Now, ultimately, voltaic cells, and this is going to start to come into play and be really important as we continue, is all about a spontaneous redox reaction. Now, don't lose sight of what that means. That means that your strongest oxidizing agent is going to be above that strongest reducing agent in order for that reaction to happen without any external input of energy. Now, with that spontaneous reaction, we can actually create an electrical current. And think about the logic of this. With redox reactions, we're talking about a transference of electrons, right? So if electrons are going to be transferred, well, of course, that relates to electrical current. Now, something that we're using constantly in our day-to-day lives, especially right now, considering that you are at home doing so much online and e-learning and with devices, etc., is batteries are a focal point, and batteries by their nature are voltaic cells. Now, the design of a battery gets pretty interesting in terms of how they're put together and how they can be most efficient and effective and safest, etc., etc. And I'll be honest with you, we would have talked about it a little bit more if we'd been in class together, but reality is some things have to be cut for us to be able to achieve a distance learning that really is something that will work for everyone. Now, here's something, though, that's really, really important for you to know. Every voltaic cell, as in every battery too, has 2 electrodes, and we'll talk more about what electrodes are, and has an electrolyte. Now, in terms of what is an example of this? Well, honestly, guys, classic, of course, is the batteries. But you've seen stuff like this even with silly stuff like a potato clock, right? So back in elementary school, potato clocks or lemon clocks were kind of a classic thing where you'd stick some little electrodes inside of a potato or instead of a lemon, and you'd end up with the ability to actually run a clock. Well, that was a simplistic voltaic cell. All right. Let's talk about the different components of this. So each of these are things that definition-wise you should have memorized. Electrode is the first one, and the key thing for an electrode is it is a solid conductor, and because it's a conductor, it can carry electrons in and out of the cell. And when I say the word cell, we're not talking from a biology perspective at all. A cell is still considered to be a single unit, but in this case, it is the single unit that is a component of a voltaic cell, a voltaic battery. All right, electrolyte is the next one. And electrolyte is kind of a familiar word when you think about electrolytes in your energy drinks or something like that. And essentially, electrolytes simply contain ions, right? Just like an electrolyte that's in your Gatorade is what it is. It's salts that are dissolved, so that's ions. Now, if something has ions, then they're going to be able to conduct, and that's the key thing. So an aqueous is in liquid dissolved in water. conductor. And the whole purpose of it is to separate those electrodes from each other. That way, electrons can travel between the electrodes. Now, within the electrodes, we have two different ones that we're going to be focused on. And these look a little bit familiar, or they should. Look at that beginning, cath versus an. Think about cation versus anion. Similar type idea, and that cathode is all about a positive end, and anode is all about a negative end, right? Here's your cathode, the positive end of a battery, and versus your anode, the negative end of a battery. Now the battery, just as it sits right now, doesn't work. But if I were to put something in the middle, even something as simple as a voltmeter to measure the voltage, and connect it as a wire back around to the cathode, all of a sudden we're going to have the ability for a current to flow. In other words, for electrons to flow from the anode to the cathode. Next little thing that's really, really important, besides that cathode being positive, is that the cathode, and I'll talk more about ways for you to memorize this, is where reduction happens. Vice versa, an anode, which is negative, is where oxidation occurs. Okay, let's look at this a little bit further. Memory tricks. It's really important that you do not lose sight of this and that you keep it straight in your head. On the PDF notes that are posted, I have these written out in full. We're just going to talk about them here. Now, look at that first one. Leo says Gurk. This is ridiculous, but honestly, I'm trying to get you to say, okay, here's a lion, and it's growling. What it stands for is you lose electrons is oxidation. Of course, we know that, Leo. And then the A stands for anode. So lose electrons, oxidation, anode. Vice versa, the GERS, gain electrons, reduction, and then the C here is cathode. So we're just adding an A and a C to the ends of our Leo GER. Here's another one, if you like this one better. This one reads anox, and anox, which is right here, your anox. And anox means anode oxidation. Vice versa, the red cat would be reduction cathode. And here's your reddish cat. It's not perfectly red, but you get the idea. Again, simply a memory trick. And honestly, this is the one that I use the most because I just find it the simplest. If you put your consonants together, then those ones go together. Cathode is capital C, consonant, reduction, capital R consonant, they go together. Vice versa, if you take your vowels, anode, oxidation, those two match. Anyway, couple different memory tricks. Key point is pick something that works for you because this is really important that you do not get it mixed up in your brains. Let's go on into the actual design of these voltaic cells. Now, in class, we would have built these and we would have tried them out and we would have looked at how much energy was actually given by the different combinations and designs. Reality is we have to take that out right now. But visualize and imagine if we could actually do these in class. Now, voltaic cells, important to note, are made up of two of the half cells. Now, each half cell individually has one electrode and one aqueous solution that's placed in, the electrolyte. Usually the way we make these things is take a metal and put it in its dissolved metal ion. And we'd use the same metal. This, for example, guys, is a half cell, right? It's not the whole voltaic cell, it's just the half. I don't know if you can quite read it, but this is copper solid. That's the metal in there. And it's been placed in a 1 mole per liter solution of copper 2+ aqueous. And honestly, that's why it's blue. Because if you check page 11 of your data booklet, get familiar with that page. I've referred to it before in reference to observations. But copper 2+, when it's in solution, creates a blue color. So that's there purposefully. All right, let's keep going into how that voltaic cell design continues. So we would have two of those half cells, and the two half cells get connected by an external circuit in order to allow electrons to flow. This wire is what you see right here. I'll highlight it out in yellow. And it's being connected by a voltmeter in order to measure how much energy is coming out. Usually when we do a voltmeter in a diagram, we do a V and then a circle. Those of you who've done physics, this might be familiar to you, with the wires coming out either side, right? That's your voltmeter. Now, we also have something extra in there that's really important for you to notice. There's a porous boundary. Porous means that it allows for the movement, and in this case, it's the movement of ions, and that porous boundary, make sure you know this, is called a salt bridge. That salt bridge is, I'll highlight it here in green, right here. And that seems kind of weird. Now, that salt bridge is not helping you to move electrons. That's what the wire does, right? The wire moves electrons. No, the purpose of the salt bridge is a little bit different. Your salt bridge is all about moving ions. And ions are definitely different than electrons. For example, if you have Na+ sodium ion, that's the sort of thing that could be moving. Or if you had sulfate, SO4 2 negative, that's the sort of thing that could be moving. All right, we'll talk a little bit more about those ions afterwards. But no, the whole point of them is to make sure that you balance out charge. Ultimately, a voltaic cell would still work without a salt bridge, but for a super short amount of time, because you'd end up with such an imbalance of charge where one of the electrodes becomes so positive in one section, the other becomes so negative, that we stop the flow. So that salt bridge allows us for a balancing of charge to allow for the continual flow of electrons. It's a pretty important thing. Okay, let's keep going here. Here, folks, is your general design of a voltaic cell. And you've got this picture in your notes, and I want you to add a few things in. Now, first thing that's really important to take note of is if this is a voltaic cell, then you are dealing with a spontaneous reaction. It's nothing that requires energy. In fact, it's quite the opposite. It's producing energy. Happens without any external addition of energy and actually produces energy. Now, electrons, this is really important, are always flowing from the anode to the cathode. So make note that this is our electron flow. Again, going from anode to cathode. Why? Well, if you remember back to what I said with your Leoa Gurk or anox, red cat, however you want to memorize it. Anode is where oxidation occurs, right? So if oxidation is happening here at the anode, then oxidation reactions lose electrons. They lose electrons, so it's leaving the anode, loses electrons, and vice versa. We know that the cathode is where reduction occurs. And reduction reactions are all about a gain in electrons, right? So they're gaining the electrons that leave the anode and then go to the cathode. That direction of flow is really key. I want you to also add in a salt bridge so that we can show what is necessary in order to maintain the flow. Now, within that salt bridge always contains what's called an inert electrolyte. And all I mean by the word that it's inert is it's not going to participate in any way in the reaction, right? It's inert. It's like an inert gas. Those noble gases are inert because they do not react. While an inert electrolyte contains ions, but it does not participate in the reaction. Now, this is important for you to know. We need to always recognize that in that salt bridge, the anions, so in other words, the negatively charged particles, will flow towards the anode. Oh, that makes sense. Anions to the anode. Vice versa, the cations, so the positively charged ions in there, are going to flow to the cathode. So keep that in the back of your head, right? Anions go to the anode, cations go to the cathode. A couple extra things that I want you to add in here. First one is we're going to call the anode substance X, and whatever metal that would be. So it's a solid. If that's substance X, then you have to put that electrode in a solution that contains ions from that metal. So in other words, we're just going to call those X+. okay? Because metals always form cations. Vice versa, if we go over to the other side, this cathode is going to be made up of a different metal, substance Y solid, which means that in the electrolyte, we're going to have the corresponding cation of that metal, Y plus. These, of course, are going to be filled in with actual metals as we continue on into our next example. All right, let's continue. So, moving on to this. This is one type of voltaic cell that we'll look into a little bit more detail to make sure you can make some sense of it. Now, first thing that I want to explain to you is, if you can see what's here, this is copper solid, and you can kind of notice the typical copper color. Now, this you wouldn't know without me telling you, but this is zinc solid. Okay, so copper solid, zinc solid. That means that in solution here, we have something with a copper 2+ ion in it. Perhaps it's copper 2 nitrate, it might be copper 2 sulfate. There's a lot of options of what we could use, okay? Similar type idea, the zinc electrode is gonna have to be in a solution with zinc 2+ ions in it. That's how these half cells always work. You put the metal into an aqueous electrolyte that has the same metal ion in it. All right, looking at this thing, how do you pick out which one is going to be the anode and which one's going to be the cathode? Well, you're going to have to make a decision in terms of which is undergoing oxidation, which is going reduction. In other words, guys, key thing is figure it out. Are you going to call the copper, for example, or the copper 2+, the SOA or the SRA? Well, you got to decide. Now, this goes back to what we were doing last week and the week before. Ultimately, all 4 of these things are guaranteed to be present. You have copper solid for sure, you have copper 2+, you have zinc solid for sure, and you have zinc 2+. So when you start glancing at your table, sorry, I was using this before. Okay, so let's go into our half reaction table, and you're going to start at the very top, right up here, and we're looking for the strongest oxidizing agent, and start scanning your way down, right? So keep looking, keep looking, keep looking, scan, 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 and you'll find that the first time that we hit our strongest oxidizing agent is right here. Oh, well, that means copper 2+ is going to act as our SOA. That's important, right? Take note of it. Vice versa, let's look for our strongest reducing agent. Our strongest reducing agent, we're going to have to start at the bottom down here and work our way up. And as we start to do that, and we follow, you hit it again pretty quickly. Here it is with zinc solid. So zinc solid is going to be our strongest reducing agent. So similar type thing, I'm going to go back to my table, or sorry, my diagram. SRA is here. Now remember what that means. The strongest oxidizing agent is always undergoing reduction. So that means this half reaction to the left here is reduction. Vice versa, zinc, the strongest reducing agent, is always undergoing oxidation. This just gave us the ability to label our electrodes. Reduction happens always at the cathode. My copper metal is my cathode. Oxidation always happens at the anode. Therefore, my zinc metal is my anode. All right, we'll practice this a little bit more. Just to take note here too, this is your voltmeter that's showing this charge right here. And that'll be the last part of this week's lesson in your 3rd or 4th podcast, where we talk about what that voltmeter's time actually means. Or not time, sorry, voltmeter value. Okay, let's move on. Ultimately, guys, just to clarify that last little bit that we talked about, and I showed you that on the previous page, is that the SOA, the strongest oxidizing agent, is in one of the half cells. Vice versa, the strongest reducing agent will be in the other half cell. In other words, they are not together in the same container, right? They are in two separate containers. And just like we were talking about previously, the SOA always undergoes reduction at the cathode. Vice versa, the SRA, the strongest reducing agent, always undergoes oxidation at the anode. All right, folks, that is going to be the end of this first podcast. Honestly, there's not a lot of questions from the actual assignment that you can do yet. I would highly recommend that you listen to the second podcast before you start going through and attempting to do questions. Talk to you soon.